Good morning, ma'am. This is Bhavya Jha from first year Computer Science and Engineering Department, and today I'm here to give a presentation on engineering physics with the given topic of Hall effect and its applications. So the subject code for this subject is 23PHY01. So moving on to the next slide, we have the outline of the entire presentation. So in the first point, we'll be discussing Hall's effect, its introduction, developments that led to Hall's effect discovery. Then we have Hall's effect statement, key points related to the statement, brief explanation of the statement, explanation of the derivation of the equation, applications of Hall's effect, and Hall's effect impact on the real world. So Hall's effect introduction. Now Hall's effect, which is commonly known as the Hall effect is a phenomenon observed when a conductor or semiconductor carrying an electric current is placed in a magnetic field perpendicular to the current flow. Now as we can see in the diagram, this effect was discovered by Edwin Hall in 1879 and provides important insights into the behavior of charge carriers within a material. Now developments that led to the discovery of Hall effect. Advances in electromagnetism. The late 19th century saw significant developments in the understanding of electromagnetism, particularly after James Clerk Maxwell's equations. Researchers were keen to explore the implications and applications of these theories. Now, the study of conductors. Scientists were investigating how electric currents behaved in conductors. Understanding the interaction between magnetic fields and electric fields became a critical area of research, driven by both theoretical interest and practical applications. So while there were many factors that were responsible, advances in electromagnetism and study of conductors were two prominent factors that led to the development of Hall's theory or Hall's effect. Now we have the Hall's effect formal statement, that is, when a current carrying conductor or semiconductor is subjected to a perpendicular magnetic field, the moving charge carriers experience a force that deflects them to the side, resulting in a measurable transverse voltage, which is known as Hall voltage. Now this voltage is directly proportional to the magnetic field strength and the current, and inversely proportional to the charge carrier density and the thickness of the material. Now the key points related to the statement. What are charge carriers? So the deflection of electrons, that is negative charge carriers or holes, which are known as positive charge carriers, under the influence of a magnetic field. What is Lorentz force? The force responsible for the deflection given by F is equal to Q into V into B. Q into V cross B actually, where Q is the charge of the carriers, V is their velocity, and B is the magnetic field. Now what is Hall voltage, that is VH? The voltage that develops across the material perpendicular to both the current and the magnetic field is called Hall voltage. Now Hall coefficient, denoted by RH, is a parameter that characterizes the material's response to the Hall effect, defined as RH is equal to EH upon JB, which is equal to 1 upon NQ, where EH is the Hall electric field, J is the current density, B is the magnetic field, and N is the charge carrier density, while Q is the charge of the carriers. Now here is the derivation of Hall's effect. So from the figure, it shows that the semiconductor carries current along x-axis, the magnetic field is along z-axis, and the produced electric field is along y-axis across other two phases, and electric potential VH is developed. Now we know that current is nothing but the flow of charges when semiconductor is placed normal to the magnetic field. Maximum force acts on charges whose magnitude is given by FB is equal to BE into VD, and its direction is given by Fleming's left-hand thumb rule. Now, according to this rule, if semiconductor is of n type, then positive charges will be deflected in upward direction and negative charges will be downward direction. So we find that the positive charges on top surface and the negative charges on the bottom surface. Now, if semiconductor is p-type, then the negative charges are deposited on the top surface and the positive charges will be deposited on the bottom surface. Now, this separation of positive and negative charges leads to electric potential called the Hall's potential across the given phases. This is given by the equation VH is equal to EH into D, which we take as equation 2. Now, where D is nothing but the thickness of semiconductor, then again we have, because of this, that is because of this Hall's effect, the negative charges try to deflect in upward direction, whose magnitude is given by FH is equal to E into EH, C into EH, where FB and FH are equal and opposite equilibrium state is reached. So finally we have EH is equal to B into VD, and we have current density J is equal to N into VD. VD is equal to J upon NE. We finally do the substitutions and we reach at the conclusion that RH is equal to EH upon BJ, where RH is nothing but the Hall coefficient. Now that was about the derivation part. If we discuss about the applications of Hall's effect, the Hall effect has a wide range of applications in science, engineering, the technology, due to its ability to provide insights into the behavior of charge carriers and its utility in sensing magnetic fields. Now, some key applications could be Hall effect sensors. Now, at the first we had a diagram, and that diagram was about the Hall effect sensor. Now, Hall effect sensors are devices that measure magnetic fields by converting the Hall voltage into a readable electrical signal. Then we have the magnetic field measurement, which is a device that is used to Gauss meter and magnetometer to measure the strength and direction of magnetic field. So moving on to the next slide, current sensing. Hall effect sensors can measure the current flowing through a conductor without direct electrical contact. We have the non-destructive testing, that is used in non-destructive testing to detect defects in conductive materials. Then we have semiconductor characterization. The Hall effect is a standard technique for characterizing the semiconductor materials. Hall effect sensors are used in various position and motion sensing applications. Now, conclusion and Hall's effect impact on real world. The Hall effect is significant in several ways, and its importance can be summarized in three main important points: characterization of materials, magnetic field sensing and measurement, current sensing and control. Now, in summary, the Hall effect is crucial for material characterization, magnetic field sensing and current measurement, making it indispensable in the fields of electronics, automotive, industrial automation and renewable energy. So this was all about the Hall effect, its applications, its derivation, what it actually is, and its impact on the real world. So with this, I conclude my presentation. Thank you. This is a presentation by Bhavya Jha, bearing the roll number 234G1A0525 from Department of Computer Science and Engineering. Thank you.